So, hello everyone, my name is Zhang from the University of Manchester. So it's my great honor to represent our research group and present our latest findings, the novel insights into quick fatigue interaction on the uncommon waveforms. So first, this study is motivated by the need to extend the operational lifespan of next generation nuclear reactors. So while progress has been made, the mechanism of quick fatigue remains challenging. So the challenges stem from two parts. So first, when the creep and fatigue interact, the deformation behavior becomes complex and it leads to a more complex failure mode. And then second, perform the creep fatigue test is cost a lot, and perform such long-term testing is also have some technical challenges with stable about the risks. So our aim is try to understanding this basic mechanism and try to optimize the creep fatigue testing approach. So considerable experimental and modeling efforts has been devoted to study the key factors such as strength range, rate, threshold duration, load waveforms, which has significant effect on the fatigue and pre-fatigue behavior. So before presenting our findings, I will briefly review these key factors. So the first is we examine the relationship between strain rate and fatigue life. So in this figure, we use a matching profile relationship to fit the data we collected. So we can clearly see that the test conducted at 10⁻³ per second, so the blue line, shows a relatively longer fatigue life compared to the test conducted at 10⁻⁴ and -5 per second. So this represents that the fatigue life increase with increase in strain rate. So then we explore the effects of tensile hold duration on fatigue life. So in this curve, we use the solid blue line serve as a baseline for the test without any tensile durations, while the dashed line represents the test with tensile duration range from 6 to 60 minutes. So clearly, when the creep is introduced in the fatigue life significantly reduced. And then we can find that the fatigue life increase with the decrease in the tensile hold durations. And then we find an interesting phenomenon is when the asymmetric load waveform was used. So first, when the slow tension fast compression was used, we can see a relatively lower fatigue life compared to the fast symmetric loading and slow symmetric loading. And remarkably, the fatigue life reduction under such condition is similar to the symmetric loading with 60 minutes tensile hold. And then, in contrast, we can find that when the fast tension slow compression was used, the fatigue life didn't reduce compared to the slow tension fast compression. So to our knowledge, there's no studies to conduct to understand such behavior from both macro and micro mechanical perspectives. So thus, our research methodologies comprise three messages. So first, we perform micro-scale experiments to study the stress-strain curves and the peak stress and the fatigue life. And then we perform post-mortem characterization using XEM fractalography and X-ray computed tomography. And then finally, we perform the in-situ neutron diffraction measurement to study the green level deformation and try to use a modeling to help understand all the experimental observations. So first, we perform 4 distinct fatigue and pre-fatigue tests, which can be categorized as follows: the fatigue SF, fatigue FS, pre-fatigue SF, and pre-fatigue FS. So all the cyclic loading was strain controlled, and the creep is stress controlled. So all the test was maintained at a temperature of 550 degrees C. So we set 2 orders of difference in the strain rates during the loading and the unloading. The strain rate here is 1 is 3 times 10⁻⁵ per second for the slow loading, and the fast loading is 3 times 10⁻³ per second. And the creep we introduced in the fatigue is 60 minutes per cycle. So here is our experimental results about the history loop of the fatigue and pre-fatigue test results. So this is the first cycle of fatigue test. So there's no clear difference, but we find an interesting phenomenon about the stress patterns. So we can find that the stress patterns is observed during the slow loading in each load waveforms. This is attributed to the dynamic strain agent and some alignment with the rigs. And then we can find more significant difference between these two waveforms by the saturation cycle. We can find that the peak stress is higher in the slow loading direction in the SF test, while it's higher in the fast tension slow compression in the FS test. And then let's look at the results from the first cycle of pre-fatigue test. The results quite similar to the fatigue cycles, but the difference is in the first cycle, we can directly see the peak stress difference. When the stress passed its yield stress of around -70 megapascal, in the FS test, it shows a higher stress amplitude, red lines, compared to the SF waveforms. And by the saturation cycle of pre-fatigue test, we can also see this difference in the peak stress. And these results lead us to examine the difference in the peak stress evolution. So here, this figure shows the peak stress in the tensile and the compressed directions in the all four tests and plotted against the load cycles. So first, all four specimens exhibited a typical stage of hardening, saturation, and softening. And the saturation stage occurred around 50 cycles after the test starts. And then let's look at the cycles to failure. From the result, we can clearly see that when the SF waveform was used, it has a relatively lower fatigue life compared to the FS in both fatigue and pre-fatigue conditions. And then we check the peak stress difference in the saturation stage. In the tensile direction, we can find that the peak stress is higher in the fatigue SF and also pre-fatigue SF, around 20 megapascal higher compared to the FS waveforms. While in the compressive direction, the FS waveform shows a higher stress amplitude, also around 20 megapascal. So this result shows that, so first, SF waveform will lead to a shorter fatigue life compared to FS. And then the slow loading phase will cause a higher stress amplitude during the slow loading directions. And then we try to understand whether the difference in the peak stress will also change the creep deformation. So here we study the deformation difference in the two pre-fatigue tests. So the first is the creep strain evolution for selected cycles. So there's no significant difference in the first cycle. So we can see the curve here. So around a fifth cycle for the solid and the dashed line is for the FS and SF. The creep strain is quite similar. But by around like 100 cycles, the blue line. So for SF test, it shows a relatively twice that value of the creep strain compared to the FS waveforms. So then we compare the peak creep strain evolution plotted against their load cycles. You can clearly see that the SF waveform, the blue line here, shows a higher peak creep strain compared to the SF waveform. That means when the SF waveform was used, it will increase the sustainability to the creep damage compared to other load waveforms. So then we try to study the fraction morphology on these samples. So we do the SEM test. So here we show the representative results for the fatigue and pre-fatigue specimen. So for the fatigue specimen, we can clearly find the correct initiation site, the yellow arrow in the top left figure, and it's initiated near surface and propagated inward, and leave a distinct region with fatigue striations. But for the pre-fatigue specimen, the feature is quite different. We cannot find any correct initiation site and the fatigue striation sites, but we can clearly see the integrated phase. So that's represented that even under the using of asymmetric load waveforms, the creep will alter the surface morphology, transition from the fatigue-dominated to creep-dominated features. And then we try to quantitatively analyze the defects inside the samples. So here we do the XCT, so it's a representative results from the pre-fatigue SF specimen. So overall, the defects range from 0 to around 400 microns, and the two magnified views, two main types of defects inside the specimen. One is cracks and another one is voids. So then we use this normalized number-based size distribution to show the defects across the four samples. And from the result, we can see that the blue dashed line, which represents the pre-fatigue SF specimen, shows a clear difference compared to other load waveforms. That means the pre-fatigue SF specimen has a more high portion of defects in the 10 to 40 microns and more presence of micro cracks. So this is all our inspections on the our micro-scale experiments and on the samples. Then we perform the in-situ neutron diffraction measurements combined with these asymmetrical load waveforms. So here we perform 4 asymmetrical load waveforms combined with this creep and to measure the neutron diffraction during the creep. And from the result, I think we measure 4 representative green family, which is 1, 1, 2, 0, 0, 2, 2, 0, and 3, 1, 1. And here we just use 2, 1, 2, 0, 0 as our representative result. So when we considering these asymmetrical load waveforms, when the slow tension was used, we can see that it will first increase the macroscopic stress, which is similar to our other results. And then it will also increase the lattice strand deviation. For example, when we load the stress to the peak tensile strand, the 200 green family has a lattice strand of 3,400, but it will increase to 3,600 after 1 hour peak dual. But following fast tension, this is SF, this is FS, the lattice strand deviation didn't change, it shows the constant. So that means the SF waveform will increase the grain level deformation incomparability when it was used. And then finally, we use the crystoplastic modeling to try to understand why this happened. So here, first, our experimental results reproduce the peak stress difference. So the left figure, it shows that a higher stress in the respective slow loading phase in the under the 2 waveforms. And then in the right figure here, we shows the total dislocation distribution across our simulated crystals. So as also shown in these simulation results, there's no significant difference in the first cycle. So this is captured during the peak tensile strength. But by the saturation cycle, we can clearly see that the SF has a higher dislocation density compared to FS waveform. So the value for this is around 180, and this is only 120. So this represents that the SF waveform will lead to a great accumulation of dislocation, which associated with the critical shear stress and lead to a higher macroscopic stress. So finally, to summary, the effects of asymmetrical waveform. So our microscale and micromechanical test shows that the SF waveform will accelerating material softening and increasing the creep damaging susceptibility. And then when we look at the test duration we used, we can find that the SF waveform only used around half or 1/3 of the test duration compared to other load waveforms. So this can be developed as a promising test approach to help us accelerate the creep fatigue test and save our time. So this is all our findings. Thanks a lot for listening.